to everyone?
Yes, sir.
All right, so DMAP is no longer being used as a good base, but when it was used, it was in fact this nitrogen which act as a base, not this nitrogen. Because the non-bonding electron pair on this nitrogen, which is sp hybridized, is perpendicular to the plane of these pi orbitals. So it cannot participate here in resonance. Whereas this non-bonding electron pair on this nitrogen, which is sp3 hybridized, you see this is a carbon nitrogen single bond. It can rotate anytime. So when it can rotate, this pi orbital can also rotate. So it can acquire the plane of this pi orbital here. So it is delocalized. So this lone pair is delocalized, so it is not available. So the delocalization of lone pair on nitrogen causes a decrease in basicity, and localization causes the increases its basicity. So this nitrogen is more basic than this nitrogen. In fact, that's why it is believed it is this nitrogen which picks up proton. That's what I have presented here. It is that base which picks up this proton, which is pyridinic nitrogen. So anyhow, this base is no longer being used due to aromatic behavior of this. Aromatic systems are carcinogenic, cancer causing. They trigger cancer. So they are not been no longer being used as system. But long time ago, pyridine was used. Pyridine also has some other than carcinogenicity. It has other effects on the male systems. So anyhow, DMAP and pyridine are no longer being used as a base. But these days, two bases are most frequently used for elimination. They are abbreviated as DBN and DBU. What this DBN and DBU stands for, this is an abbreviation. This is the actual structure of this molecule. You see, both of these two contain six-membered ring. This is a six-membered ring where nitrogen is present at 1,3 position, and here it is a 5-membered ring, here it is a 7-membered ring. This is the only difference. Rest of 6-membered ring, 6-membered ring, same double bond position, etc. But having this is a 7-membered ring, this is 5-membered ring. There are two carbon additional in this system. This is the only difference. There is no other difference at all. So the numbering always starts from bridge head position. This is a bridge head carbon, this is a bridge head nitrogen, but nitrogen shall be favored because this is a heteroatom as per IUPAC rules of nomenclature. So this system, this nitrogen shall be 1, 2, 3, 4, 5, and this nitrogen shall be 6, 7, 8, 9. So there are total 9 atoms in this bicyclic system. That's why this is called nonane. But it has a double bond between atom number 5 and 6. So this is called non-5-ene. Mean a double bond at 5 position. So this is nonene. But how we name the simple systems, we normally use bicyclo because two rings are there. This is a two fused ring system, 6-member and 5-member. So we use normally bicyclo. So there are 3 atoms on one side and 4 atoms on the other side. So 1, 2, 3, 4. 4 one side and 3 other side. So 4.3.0. There is no other atom in between. So this is, if there is no nitrogen at these two positions, this is bicyclo 4.3.0 non-5-ene. But because there are two nitrogen, we are supposed to present the position of nitrogen. So it is at 1 and 6 position. That's why we write 1,6-diaza. Aza because of these two nitrogens. Diaza bicyclo. Now this is a complete name. IUPAC name 1,6-diaza bicyclo 430 non-5-ene. So this is abbreviated as D, bicyclo B, and nonene, because nonene and undecene, these two are the variations. So that's why DB are the same, common among both, which is but the position of this ASA is different. In this system, you see numbering shall be started from heteroatom. So 1, 2, 3, 4, 5, 6, 7, 8. This atom is number 8. So 7 position, in fact, we are having, I should write here, one A diaza, because carbon number 8 is replaced by nitrogen. So this is 1,8 diaza bicyclo. Maximum number of atoms are this side, which are 5 greater, and then there are 4 other sides 0. So this is 4.3.0. This is 5.4.0. It is in descending order always. And undecene, 7 undecene. So 7 is showing the position of double bond. 11 number of atoms whenever you have in a system, it is called undecane. 12 are called dodecane, terdecane, tetradecane, pentadecane, etc. So undecane show 11 atoms. So there are 11 atoms in fact here. So this is a DBU, this is a DBN. Both are very similar. The 6-membered ring is common among them. Same position of nitrogen, same double bond, but only difference, we have a 7-membered ring here, we have a 5-membered ring here. And the mechanism of action is also same. So if either you are using DBN or you are using DBU, it doesn't make a big difference in fact. Now, how we carry out this reaction? This reaction is very similar. In fact, let's see if I present here how it mechanistically undergoes. Now, first of all, look at here. This nitrogen lone pair, very similar to pyridine. This nitrogen is sp hybridized, and this nitrogen is sp3 hybridized. So this lone pair present on this nitrogen is delocalized to this double bond. It donates electron pair here, and this electron density transfers on nitrogen, generating a negative charge on the nitrogen. So this nitrogen positive charge, this nitrogen negative, this is the other resonance form. It means this lone pair is involved in resonance, so which causes a decrease in the basicity of this nitrogen. Look at the other nitrogen. This is the other nitrogen. In this nitrogen, we have a lone pair which is present on sp hybridized nitrogen. So this orbital is at position this, which is in the plane of this board, but nitrogen here have a pi orbital which is perpendicular to this plane, and same is this one. So this is along the plane. So both pi orbitals on nitrogen, on carbon, and this system, they are perpendicular to each other. So when they are perpendicular, so it is not available for resonance. This is the reason this lone pair makes it feasible for, it is more basic nitrogen as compared with this one, just like we have seen in case of DMAP. This nitrogen lone pair is delocalized, this is not delocalized. Same, this lone pair is not delocalized, this lone pair on nitrogen is delocalized in fact. That's why this nitrogen takes part in reaction. It acts as a base, it donates electronic density to this proton, X leaves, and we result a double bond at this position. All right, this molecule is being generated, and what we get, this nitrogen is protonated. Once it is protonated, it is positively charged. It takes this pi electron density towards this to generate a positive charge there, and then this nitrogen donates this electron pair here to generate a double bond here with positive charge. So these are the 3 resonance forms possible in this case. One is in which we have protonated nitrogen, second in which we have a double bond here, third in which we have a positive charge here. So positive charge on nitrogen, positive charge on this carbon, positive charge on this nitrogen. These are the 3 resonance forms. So this is how, now let's see, in other resonance form, this nitrogen shall pick up electron pair generating a positive charge here. Then again, nitrogen shall donate electron pair back here, generating a double bond. 4 bonds making positive charge. So 3 resonance forms are possible in this case. Either this is DBN or this is DBU. Both of them undergo very similar reaction and results in this. Let's say if this nitrogen is going to act as a, so look at this nitrogen. This nitrogen is a bridgehead nitrogen. You have seen already substitution reaction. Bridgehead systems are always physically too much crowded. When they are too much crowded, so they are not available for substitution. So this nitrogen is already poor base. It cannot act as a good nucleophile. This can act as a nucleophile. Let's see if it is transferring, it shall generate a positive charge on this nitrogen substituted with X. So it shall not be stabilized. That's why it shall reverse back. So these DBN, DBU, 4D map, etc., they are the very good bases, especially used for elimination. If we are using DBN or DBU at high temperature, it definitely prefers elimination, no substitution at all. So substitution can be made recessive by making use of a good base and at doing the reaction at high temperature under thermodynamic conditions. So I hope it shall be very clear for you right now how we can facilitate elimination. So using a very good base, poor nucleophile, and making use of a high temperature. These are the two factors in our hand that we can exploit and carry out elimination, dominating over the substitution. Right, so these are the two mechanisms you have come across about the solution phase chemistry. Mean when over substrate, over base, all of them are in solution phase. A third one is called E1cB. No doubt this is E1 as well, but conjugate base. CB stands for conjugate base. So what is E1cB mechanism? This is entirely different. Just review. You have seen in E1 elimination what happens. First step is a slow rated step. A carbocation is generated as an intermediate. And in next step, we get the olefins. So look at this E1cB. This is entirely opposite. The first step is also slow. The second step is fast, very similar to E1. That's why it is have a, we call this E1cB because it has first step slow like E1, second step fast, but it doesn't involve the generation of a carbocation. Look at here, this is totally opposite. What happens in E1, first this group with which is a good living group leaves first, and then the base pick up this proton generating a carbon-carbon double bond. So we get a carbocation generation as an intermediate, but what happens here, it is opposite. First we get a base pick up a proton generating a carbanion, and then this carbanion donates electron density here and transfers the X leaving with electron pair. So this is totally opposite. The second step which happen in E1 is happening first, and the one which happened first in E1 mechanism is happening later. X is leaving second, but base is picking up a group without electron. You see base is picking up this proton, a group is leaving without electron pair first, then a group is leaving with electron pair later. But in E1 mechanism, this is opposite. A group leaves with electron pair first and a group leaves without electron pairs later. This is totally opposite. Here we get a carbocation generation, but you see in this case we are getting a carbanion is generated. This is totally opposite. Let's see if I exemplify this reaction. During one of our natural product synthesis, we have synthesized this compound number 9 from 5. How? This was not an easy task to bring a bromine. It apparently looks like very simple to replace this hydrogen by bromine, but it was a very, very difficult task. We have used so many reagents, but anyhow, we finished to this one. Bromine is added. Bromine to olefin. This is an olefin. Bromine, whenever is added, if you remember, this is always a Ei addition. If this bromine is above the plane, this bromine shall be behind the plane. If this is behind the plane, this shall be above the plane. That's why I have not presented the stereochemistry of this. No doubt, both bromine shall be opposite to each other. So if this is above the plane, this shall be behind the plane. If this is behind the plane, this shall be above the plane. Totally opposite to each other. So this is why we know that this is a cis olefin. Whenever anti-addition takes place, it always result a trio product. So these two groups should be opposite to each other. So I haven't presented because two isomers are possible. So that's why I have generated them. They are totally opposite to each other. Now what happened in this case? First of all, the base reacts. Do not forget, this system also exists in enol form. I have presented the enol form. This is the enol form. You see, this is enol. Base picks up this proton, enolic hydrogen, which generates a positive negative charge on this oxygen, and base picks up this proton, the very first step. All right. So we get an inlet here. So once we have an inlet, beta position, this is alpha, this is beta, we are having a bromo position. So this oxygen is donating electron pair density here. This pi electronic density is transferred here, and this bromine leaves with electron pair. So what we get in this case, this bromine is leaving a new carbon-carbon double bond generating, and carbonyl oxygen is taking pi bond again. So this molecule, this one, this double bond is same, but this hydrogen is replaced by bromine. How this hydrogen is actually enolic hydrogen. All right. So this enolic hydrogen is replaced by bromine. So this is the in fact protocol. First is addition, next is a elimination, but this is involving E1cB mechanism. You see, first we are using a base. So normally when we are having this R1 or R2, if they are pi electron density, mean they are carbonyl, they are nitro, they are iminic, etc., then E1cB mechanism is possible. If you have only alkyl groups present here, then E1cB mechanism is not possible. You must have an electron withdrawing group present by inductive effect and by resonance at this position. So then it shall be possible. So there is a substitution taking place at this system. This group is leaving with the electron pair, and it is generating a double bond. This is eliminating, and you see a hydrogen is eliminating from this position, hydrogen from here, and we are, but this hydrogen is not itself eliminating, it is in enol form, that's why it is eliminating. Base can pick this up in fact. So this is a E1cB mechanism. All these three mechanisms, either E2, E1 or E1cB, this takes place in solution phase. Whenever we are having our substrate and our uh, base in solution form, mean dissolve in a solvent, we are heating this and we have a good base, DBN, DBU we are using, then we shall follow any one of this, E1, E2 or E1cB mechanism followed. It depends upon the structure of the substrate. I hope it is very much clear right now, but I shall switch over right now to the gas phase or vapor phase eliminations. Vapor phase, what we are having, we have our substrate, we have no nucleus, we have no base in fact, only substrate. We are heating the substrate to a very high temperature. So what happened, it undergoes syn elimination. The group which undergo anti-elimination, you have seen a list. Let's see, I have given a list which undergo anti-elimination. All these groups, when in gas phase or vapor phase, they undergo syn elimination. I have presented this. This is called EI, elimination intramolecular. You have already come across this. We don't need any base. This is very similar to SNI mechanism. In SNI mechanism, if you remember, we don't have any nucleophile. Nucleophile is present within the molecule. So very similar is here. Let's say if you remember this acetate moiety, ester group. This ester group always undergo anti-elimination, but when we are carrying out this reaction in vapor phase, it always undergo EI elimination. I have presented the mechanism of this. You see, this is one of the components, hydrogen, and this group are eclipsing. Why it undergo? Because there is no base used here. Base cannot pick up this hydrogen. So this hydrogen is picked up by this oxygen. It transfers this pi electronic density here to generate a single bond between hydrogen and oxygen. And at the same time, this pi electron sigma bond transfers here to the positive charge going to generate here. So we get a carbon oxygen double bond at this position, and then hydrogen leaves without electron pair. This is how a double bond is generated, and we get this olefin. I have presented this in a different form. You see, this is a chair conformation. You see how many atoms are involved: one, two, three, two carbons, four, five, and six hydrogen. I have presented all of them in this form. This is a chair conformation. Pi electronic density transfer, a new bond is formed between oxygen and hydrogen. This sigma bond transfer here to generate a new pi bond. All right. This sigma bond breaks up, and this sigma bond breaks up, transfers electron density here, generating a new pi bond. A pi bond is generated here, a pi bond is generated here, and a sigma bond is generated here. It generates a carboxylic acid following this transition state. You see, this bond is breaking, this hydrogen carbon bond is breaking, this oxygen carbon bond is breaking, that I have presented in red. And this oxygen carbon pi bond presented in green, this is going to form. This bond between oxygen and hydrogen is going to form. This carbon carbon double bond is going to be formed. So it is following this transition state, generating this entity. So this is an intramolecular molecular elimination, in fact. So nucleophile is present within the substrate. You have also come across sulfonates. I have presented here an example. R, S double bond, O, O. This R is variable, if you remember. This may be a simple phenyl. This may be a tosyl. And if you remember, this group may be uh, 4-bromophenyl. It may be 4-nitrophenyl. It may be CF3. It may be C4H9 nonylate, etc. So it may be any. This R is variable in sulfonates. These are sulfonates. I have presented the chair conformation of this, in which we have very similar. Here it is carbon, but here this is sulfur. Here we are having this carbon directly attached this, but this sulfur, you see, 4 bond. At axial position we have sulfur oxygen double bond, and at equatorial position we have alkyl group, because alkyl group is typically more crowded. It is equatorial. So this oxygen sulfur bond is axial, and this is along this plane. Now very similar, these bonds are going to be formed. These bonds are generating between oxygen and hydrogen. This bond is new bond is forming, pi bond is forming, because this bond is breaking, a new pi bond is forming here. So this sigma bond is breaking, pi bond is generating here. This is a transition state. So this is going to be formed. In fact, these 3 bonds, very similar to these, are again going to be formed, and these 3 old bonds are broken. All right. So these 2 are going to generate the product number 2, which is this one. So both mechanism, either this is sulfonate, a good living group, this is acetates. You have already come across xanthates and tertiary amine oxides. They already undergo syn elimination. So either they are solution phase or they are gas phase. They shall always undergo syn eliminations. So if our Greco elimination, for sulfoxides, seleno oxides, they all undergo syn elimination either in solution phase or in vapor phase. But the group which undergoes syn anti-elimination in solution phase undergoes syn elimination in vapor phase. This is the interesting feature that you should remember. This is called Ei elimination mechanism. So I am not focusing at the moment on free radical mechanism, because free radical chemistry is included in your syllabi reaction mechanism course that shall be offered in next semester. So that is completely discussed there, all kind of substitution. But free radical mechanism, if you remember, follows 3 steps. One, initiation, in which we need a free radical initiator. which generates a free radical. This free radical adds to a system and undergo propagation step. In last step, you can have two free radical combining with each other to form a neutral entity, which is called chain termination step. So these three steps are all involved in all free radical mechanism, but this is not included in your syllabi at the moment. You shall see that in next semester in reaction mechanism course. Right, so a few applications in this case where we are short of time. We have around 6 minutes remaining. I shall focus on this. Let's say we have these two substrates, this substrate and that substrate. Look at here. In previous semester, you have seen the decalene system, fused ring system. This is decalene. This is decalene. Two benzene rings, two cyclohexanes are fused. Two cyclohexanes are fused. It has similar. This is deuterium. This is methyl above the plane, methyl behind the plane, methyl above, behind deuterium. These three have same configuration, but configuration is changed at this position. You see this bromine and this bromine, they are different now. So you can see these two are the isomer. When we undergo them elimination, one of them, this substrate reacts, this doesn't react under elimination. Why? Because this is a trans ring junction. You have studied in previous semester that in trans decalene doesn't flip over. This is the trans-decalene. These are two benzene, two cyclohexanes fused with each other. This is the methyl pointing above the plane at bridgehead. This methyl is axial position behind the plane, which is totally opposite 180 degree to each other. So at this position, leaving two carbon, we have a deuterium is above the plane and protium is behind the plane. So this is axial, this is equatorial. So what happens in this case? Bromine is above the plane, so this is axially position. Now bromine, this carbon is quaternary carbon. It has no hydrogen. It doesn't undergo elimination. But you see on the other side, we have an axial hydrogen which can undergo elimination. So if this bromine is leaving with electron pair, this hydrogen leave without electron pair, a base pick up this proton. So I haven't defined, you may use DBN, you may use DBU. So we shall generate, it shall generate a double bond at deuterium. Deuterium is not replaced. But let's say if we have the other isomer in which bromine is behind the plane, if it is behind the plane, so it shall be equatorial position. Now this ring cannot flip over. If it cannot flip over, so this bromine cannot go to axial position. So it shall not undergo elimination. So this isomer, these A1 and 2, they are epimers of each. So structure number 1 shall undergo elimination, resulting a double bond at this position. And this system, which is the epimer of this one, it is not undergoing elimination. So look at the another aspect. Let's see, this is again two decalene, decalene. This is another decalene system, but this is not a trans ring junction. This is a cis ring junction. In fact, this is also a cis ring junction. In fact, so cis ring junction can flip over. Now you see, I have presented the structure number 3 in this conformation. This is a conformation. These two rings, methyl and hydrogen, you see both of them. This is axially upward. This is equatorially upward. Both are above the plane. All right. So deuterium is above the plane. Hydrogen is behind the plane. This group is above the plane. So this is at axial position. But it is acquiring. This is donating this electron density between hydrogen and oxygen. This is making a 6-membered ring. Another chair conformation, in fact. So it shall result a double bond at this position, mean a double bond here. Deuterium shall retain there. But look at here, if this group is below the plane, mean at axial position here, now on one side, this group is, in fact, you see, this is not axial, truly axial position to this. So it is not going to generate a double bond here. Bridgehead carbon never undergo to form a pi bond. If you remember, you have studied in substitution reactions already. So this hydrogen, this is the group which is present in this position, and this group is opposite. So this deuterium, this group shall leave with electron pair, and this deuterium shall leave without electron pair, generating a double bond here. But these two products shall be different. Here we have a deuterium retained here, hydrogen is replaced, leaving. Here deuterium is replaced, hydrogen shall be leaving. We shall have a double bond here. Both shall be reacting. Both of these two are reacting, but they are not undergoing very similar mechanism. So both undergoing, it shall generate a double bond here, deuterium intact, it shall generate a double bond here, but hydrogen shall be here. Protein. A last example to present in this case is these two isomer. Now you see their conformation, they have same substitution. If let's say we are having this double bond here, we add bromine, bromine shall be added opposite to each other. So this bromine and that we are remaining